Hey guys, we're going to get started. Thanks again for coming. So just a few announcements before we get started. First, we have meetups coming up next month. I don't know if you guys saw it, but we're going to have a Hive meetup, a Hadoop operations meetup, and then there's the HBase meetup. And there's also another Spark meetup coming up in February, again by Chris from Databricks. So he's the author of manning Spark in action as well as effective Spark. So that'll be another great meetup for you guys to attend. The next thing is I just want to introduce Byron from Rubicon project. Byron and Rubicon were gratefully helped us, to set up this event at the very last minute. So just a quick round of applause for the Rubicon project in helping set this up. So Byron is going to just make a few announcements from Rubicon.
Thank you, Subhash. Thanks so much for organizing this, and we're just thrilled to be hosting. I wanted to just thank everybody for coming, and for the Rubicon project employees watching, I wanted to let you know a little bit about what we're doing on Spark. We are currently using Spark. Our BioCloud team is using it to do some really fast-paced analytics on some of the data that they're generating off of the bidder. But we are looking to expand our footprint a lot. Currently, we're sort of running a 2-node standalone cluster. My announcement for this evening is by the end of the year, we're going to have a 100-node Spark cluster up, ready to go, available for developers to start real work at scale. And so I'm really thrilled that Paco is here tonight to tell you a little bit about what Spark can do in Spark Streaming. And yeah, thanks all for coming. Back to you, Subhash.
Thanks, Byron. So Byron promised me he's going to expose the Spark cluster to anyone who wants it. So Byron, did you agreed on that, right? Remember? Absolutely. Yeah. Okay. So send us a link. Don't forget. Will do. Okay. So with that, I just want to introduce Paco and Samir from Databricks. I've been trying to get Paco to come down for such a long time, and actually all this got set up through Adam. I forget how to pronounce his last name. But Adam, if you're watching this, thank you again very much. He's the one who actually got this set up. He works at Esri, and he kind of facilitated this entire process. So I want to thank Adam, and then introduce Paco, and then maybe Samir will probably come down and do a short presentation later as well. So quick round of applause for these guys, and thanks again.
Thank you. Appreciate it. All right. Thanks so much. Not sure how to turn this on. That looks right. Is this? All right. Can you hear me okay if I'm talking this level? Is it coming across on the mic? All right. Thank you very much. Thank you, Subhash. Thank you, Adam. We just saw him a couple hours ago. And thank you, Byron. Really appreciate here Rubicon Project hosting us. My name is Paco. I'm Director of Community Evangelism at Databricks. And I'm here with Samir Faruqi, also on the same, we work on the same team, training and evangelism. Samir is also a solutions architect, working on both teams. And so we'll definitely try to carve off a lot of time tonight to do Q&A, because I think, especially with both of us here, we can cover a pretty broad range of questions for Spark. So our boss always asks the same question. One thing I want to check in is, like, how many people here, number one, are using Spark already? Okay, cool. And are planning to? How many people are planning to? Okay, excellent. Out of that, like, what kind of background do you have? How many people have done work with Hadoop before? Okay, interesting. Like, okay, interesting. And the other thing would be languages. We're really curious. How many folks come from working with Scala mostly? Oh, excellent. How about Python? Okay, definitely. And Java? Any others? R? Okay, good. Good stuff. Okay, those are good numbers. And for the last survey, the one that's really interesting is how many people come from a background of more, say, data scientist, analyst kind of background? Analytics. Okay. What about application developers? Interesting. Okay, cool. That's definitely had a much more uptick. How about more from, say, DevOps operations? Okay, cool. How about system architects? Really? Okay, great. Okay, this is giving us good feedback. And last but not least, product managers, program management. Good stuff. Okay. We were trying to figure out like what the audience is, because what we see with Spark is that this does cut across a lot of different kind of roles, and we're really trying to understand, especially for the training and other materials we put out there, you know, how to tailor that. So for a little bit of background about Spark, it came out of something called AmpLab at Berkeley. It was formerly called RadLab, and Spark had actually started out from a project that I saw in its infancy. It was originally called Nexus, and Ben Heinemann had been leading that. He'd finished up at Washington and gone to Berkeley, and he was working on cluster management, and they had a lab there with a lot of PhD students and about 9 Linux boxes, and they wanted to have a way to let people share the Linux cluster and run Hadoop and run MPI and run a lot of other things for HPC. So they started working on this project, and it was later called Mesos. So anybody here done Mesos work? Excellent. I used to be on the Mesos project before this. And once they had Mesos up and running, there was one spring break where Ben took a bunch of the folks from the project back to his family's cabin it's near Aspen, and they watched like Firefly all week and coded, and they came up with this sort of new framework to show off what you could do with Mesos, and that was Spark. So Matei Zaharia was the lead on this, and that came out of 2009. It went into open source in 2010, and it's had this remarkable growth. I'll show some curves. It went into incubator status in Apache, became top level earlier this year, and then went to 1.0 before the middle of the year. And it was all kind of like in record time. It's just had this enormous growth. I've got a quote here from Gartner. I really hadn't expected to see anything from Gartner about Spark for a while. They usually take a little bit before they evaluate. But you know, it's a lot of what we're seeing is that this cuts across, you know, ETL, analytics, a lot of different areas of what you'd be doing with big data. So the idea is that you've got a common core engine, and it's more flexible, more general than what we were doing with Hadoop before. Some of the constraints of Hadoop have been backed off so that we could handle a more general range of use cases. And I'm not going to go into too much detail on that, but it's basically, you know, Hadoop came out of work in 2002. Google was doing MapReduce back in 2002. And the kind of things that you would see in a data center in 2002 versus 2014 are dramatically different, right? Now we've got multi-core, big memory spaces, you know, much faster networking, SSDs, all this. So generationally, Spark is leveraging newer kinds of hardware and really taking advantage of that and relaxing some of the constraints that Hadoop had. And by virtue of that, then, you get the ability to run a lot of different types of use cases on top. Spark SQL, streaming, MLlib, GraphX, a number of different things that if it had been just based on Hadoop, you'd have to have specialized clusters for these different things. So a lot of what Spark is about is being able to take workloads that might require some SQL, maybe you're doing your ETL, and maybe some streaming, bringing in some other data, maybe some machine learning, some graph algorithms, et cetera, bring it all into one app and not have to have a lot of specialized clusters, not have to learn a lot of different systems. So it's that generality that has been a really big draw for Spark. Plus, it also runs a lot faster. So the big things are it leverages a lot of in-memory compute. You know, I don't know, it's kind of a misnomer in some ways because Hadoop is really computing in memory. I mean, you lift up in the map phase, you lift up the data out of disk into memory, do your compute, shuffle, reduce, drop it back into disk. The difference being that Spark is really built for a newer generation of hardware where you have these big memory spaces, probably more than you'd want to put into one JVM even. You know, looking at like 80 or 100 or 200 gigs of memory. How do you really take care of, how do you take advantage of that? And that leads to, the bottom point actually is about how Spark leads to a lot more ease of development. We can see side-by-side code that's written in MapReduce API. I've done a lot of Hadoop MapReduce coding, my teams have, and it's fun, but it's a challenge to think about complex problems in terms of maps and reduces. whereas with Spark you get much more of the functional programming just leads to a better idea of workflow. So kind of proof in the pudding here. If you look at word count that ships with Hadoop, that's about 53 lines of Java. And Dean Wampler from TypeSafe was commenting recently, the style of coding actually reminds us of enterprise Java beans. It's sort of like at that level of all the details you have to take care of. You can do the same thing in Spark, in Scala, in 3 lines of code. And so we see that across the board, that there's a really dramatic reduction in the amount of code volume for applications. And that has a lot of benefits. In a team context, it's a lot less expensive to maintain a smaller body of code. It's a lot easier to do more complex kinds of analytics, too. One thing that happened recently is we broke the world record. So Yahoo had previously had the gray sort challenge record for 100 terabyte sort. And the Databricks team was using Spark. We're able to break it with significantly less resources. So Yahoo had used over 2,000 nodes in a cluster, and they had run that in a dedicated data center. They hadn't really announced a lot of the details of what kind of hardware they used. But they went at a certain rate. We were able to run in 1/3 the time, using 1/10 the size of the cluster. And we were using AWS EC2 nodes, so it's something that's repeatable. There's really only about 3 pull requests that went into any kind of changes to make this happen, and those pull requests are being moved into Spark Core for like 1.2. So across the board, it's about 30x improvement over what they had done before. A lot of that has to do with a better kind of shuffle and doing much less overhead, much more higher performance shuffle, taking advantage of large memory spaces. In terms of what we've seen in the open source, you get this kind of hockey stick effect. The green line is showing there is a lot of growth in Hadoop, but side by side with Spark, we're seeing like exponential growth over the past few years. And that's also showing up, Ditanami published this, where just looking at the web trend popularity, it's also surpassed that. And last but not least, this is something O'Reilly came out with, just taking a look at like what the relative median salaries are for different types of open source big data. So Spark is definitely trending pretty well there. I definitely heard, though, that if you look at the size of those confidence intervals, there is a lot of overlap. But anyway, it's still a nice trend. OK, so let me cut into streaming. I'd like to talk a bit about streaming. And by the way, after we do streaming and some demos, we've got some other things to announce, too, and then we can open up to Q&A. So focus on streaming a bit. Why streaming? First off, because since the late 90s, we've seen this huge uptick in machine data. One of the things about e-commerce was there's a lot of log files, and we can use them. We can do aggregation of log files and data mining on log file aggregation and build classifiers and recommenders and make web apps smarter and make companies like Amazon and eBay, Facebook, LinkedIn, et cetera. So streaming has to do with this huge amount of machine data coming in, and it's just growing larger because of all the sensor data that's available, all the remote telemetry, et cetera. Definitely, I would recommend this if you haven't seen it. Google has a paper called Millwell. They have a system called Millwell, but they have a paper out about it, and they have some internal use cases that they show how they're implemented in Millwell. They talk about it as a case study. Millwell describes something called microbatch, which is what we're doing with Spark Streaming. So they're very comparable kinds of systems. The other thing is that, as I mentioned, there's a lot of sensor data. So IoT, of course, is driving a lot of uptick in what we're seeing with streaming. Here's one of my favorite IoT examples here, basically having a cocktail mixer that's plugged into your smartphone. But yeah, certainly. Internet of Things, Internet of Everything. The idea is that there's more and more types of sensors and telemetry coming off of devices. I mean, here I'm being kind of facetious talking about mixing cocktails. But realistically, you're seeing sensors and interesting sensor data all over the place. Whether it's health sensors, medical sensors, or actually the next slide is probably proves the point. There's a great article here about GE, where they've got sensors on any major rotational devices. So for instance, aircraft turbine, you have to monitor the bearings because obviously if that goes out in flight, that's a very bad thing. They're getting 12 exabytes per day just for commercial flights. And the question is like, where do you take that data? What do you do with it? Can you put it in a warehouse and then do it in batch? That's enormous. I mean, it's like thousands of times the size of Facebook. So the answer is no, you really have to do it in stream. And that's why streaming becomes much more interesting. That's just one product at GE, and there's so many of them. So there's a lot of reasons for streaming. Now, Spark Streaming, we want to set some definitions to describe what it is and what it isn't. Definitely, when you talk about real-time analytics, there are so many different definitions for real-time. If you're on Wall Street and you're talking to people who are monitoring the ticker and they're working in high-frequency trading, real-time involves using FPGAs and microsecond rates. There's the catchphrase that if it hits RAM, it's too late. And they look at things seriously like that. We're not talking about that kind of real time. We're talking about streaming where usually the latency is in the range of seconds. And for such a broad range of use cases, that is really the requirement. Particularly if you're talking about streaming and doing analytics on a cluster. If you're working at network speeds on a cluster, about the lowest latency you're going to see is half second, 500 milliseconds. Below that, the network speeds just really don't work out, at least not yet. As far as the size of clusters, whereas we see Spark production apps running on thousands of nodes, like for instance eBay has a case study about a 2,000 node cluster, for streaming we're generally talking about hundreds of nodes. And the streaming requirements, you don't really want a huge cluster. You just want to ingest the data, do something important with it, and then move it off and do your analytics on it later. One thing that we've definitely seen from a lot of companies is that there's a need to look at the data when it first comes in off the wire. And if it is an outlier, if it is an anomaly, take action. But then you also want to store the data and run some kind of analysis over history, do some kind of batch. So we do see a need for taking a look at the data at least twice, once in an online context and once in an offline context. So it makes sense to be able to run the same kind of business logic in both contexts. And that was one of the real driving motivations for Spark Streaming. The other thing is we're talking about commodity hardware, clusters, things fail. Here's a question. If you've got a 2,000 node cluster, how many servers would you expect to have fail per day? One, okay. How many other takers? 100? Somewhere in between the 20? Okay, we're getting in the ballpark. So Google published this recently, and their average failure rates run 10 servers per day if you've got a 2,000 node cluster. And that's Google today. So efficient recovery from failures, that's a hard problem. Doing streaming on a cluster is a hard problem when you've got fault tolerance as a requirement. But that's one of the things we're really trying to work towards. So the idea of streaming is you've got this live data stream, and you can cut it up into batches, micro batches, again, on the order of seconds. You cut it up based on the time windows. And any data that comes in during a particular time window, during a micro batch, that's the data for an RDD. So the main data abstraction in Spark is something called an RDD, a resilient distributed data set. And you can think of it as a collection that's out on the cluster, and it's partitioned out on the cluster, and you can apply functions to it to get some kind of work performed. So here, in streaming, it's working much the same way as Spark does, Spark General, or Spark Core, I should say, that you've got this RDD and you apply functions to it. And this leads into a really good way then to be able to combine processing for both your real-time feeds, your streaming feeds, as well as your historic data. So being able to blend streaming with batch, that's very important. You could think about having what you're bringing in over Spark Streaming, having RDDs for the different time periods and some kind of window that you've kept of those in memory, but then being able to take that and union it with some other window that you have on disk. That way you can adjust how you blend the most recent data with some historical data. If you take a union across a bunch of RDDs, you get one RDD, and then you can apply your business logic to that. Now, there's a lot of different ways you can bring in sources onto Spark Streaming. There's very sophisticated work with Kafka, with Flume. We have utilities for also bringing in off of Twitter API, and I'll show a demo with this. Or you could come off of message queues. I can show a demo also with TCP sockets, just kind of a real simple case, but it's good for testing out things. The project itself started in 2012, so it's a couple years later than Spark Core. Tathagata Das is the lead on this, TD, and here's his photo. The project really got out into the wild in 2013 and then became part of Spark proper in 2014, this year. The paper is referenced from 2012, discretized streams. So you hear us talk about D streams, that stands for discretized streams. And that's the microbatch. The types of applications, when you look at the use cases, we're definitely seeing a lot of work on monitoring data centers. Very interesting work there. Of course, a lot of ad tech, bid system optimization, funnel metrics, other e-commerce like anti-fraud, a number of different types of telecom applications. Also, what's interesting is a lot of the early adopters seem to be working more in video analytics, video transcoding and video analytics. And now there's more of an uptick in different types of industry, manufacturing, different telematics coming off of manufacturing. So if you want to deep dive on this, there's some great links here. The programming guide is the first link. TD also has a couple of presentations that I highly recommend, one from Spark Summit and then another one on SlideShare. And we've got a reference app. It's meant to be a Spark streaming application that you can pull off the shelf and repurpose for production apps. So I'm actually going to show that in a demo. Let me show a bit of code, though, because the way that a Spark streaming application is structured is really important. At the top of it, we're bringing in the streaming libraries. We're doing implicits there in Scala. And then we've got a line that says val SSC, where we create a Spark streaming context. And for that, we have to wrap a Spark config or a Spark context. And we also give it a parameter of the time window, a microbatch window, in this case, 10 seconds. Once we've got that variable SSC, everything else hangs off of it. So the first thing we do is create a DStream. We basically create a receiver defined off of that Spark streaming context. In this case, the receiver is just going to hook up to a TCP socket. So it needs to know host and IP. And then the next few lines are a word count. Basically, whatever comes in off that stream for every microbatch window, it'll generate an RDD called lines, and then it'll apply a word count to it and print out the results. Now in Spark, we have the notion of something called lazy evaluation. You don't actually run the code until you hit an action that needs some data. And that's true here as well. So for instance, where it says word counts print, that would be an action that triggers all of this to run. But in Spark Streaming, one of the important things is none of it will run until you hit sc.start, where you start the whole streaming mechanism. I'll show some demos, but first off I want to talk about use cases. And this is important, it's pretty new. We got permission from Netflix to start at least mentioning, they'll come out with a case study before long here, but Netflix is one of the larger production use cases. As well as Cisco, there's a use case out of MapR. There's another one, I'll show a couple of other big ones here. Pearson just published last Friday. Pearson Higher Education has a large streaming application that they're using, Spark Streaming, in conjunction with other open source projects. And another one, Stradio, I'll show a case study about that. Yeah, actually, Stradio just actually met with some of their folks in Madrid. They do a product called Stradio Streaming. It has Spark Streaming in it, along with Kafka and other open source projects integrated. But the interesting thing about it is that they put complex event processing on top. They have a CEP engine called City. And so this allows you to have the scale out of Spark Streaming, but then be able to do CEP queries on top of it. And for a lot of use cases, that's really important because CEP has been around for a long time. and a lot of enterprise uses this. So it's a very nice blend of those both worlds. I think that Stradio is probably one of the most sophisticated applications that I've seen for Spark Streaming, and they've written a lot about it. The other one is Pearson, and again, this was just made, well, we just did a joint blog post with them, but it's got Kafka, Spark, Cassandra, and they're also using Blur, which is a new project in Apache Incubator. They run this in the cloud on top of a Yarn cluster on EMR. And what's really interesting is that they had been using Storm before, but by virtue of having this kind of generality where you can run Spark to do graph and SQL and streaming and machine learning, et cetera, that was the main reason for them to replace Storm and put streaming in instead. Also, they just did work. It won't be going into Spark 1.2, but it should be going in later. Previously, we had used the high-level Kafka consumer for Spark integration, and Pearson went and did the work to use the low-level consumer, so much better granularity. Another use case I'd point to is Uyala, and they're down the street from where I live in Mountain View. They've been doing a lot of interesting work with Scala, Spark, Mesos, Cassandra, et cetera, for a number of years. They do video analytics, like for Bloomberg TV and others. But this is pretty good because it was one of the first published case studies of Spark Streaming on top of Yarn. And so it really goes into detail about productionizing it. And another one I'd point to is Guavas. They handle 50% of US mobile data, doing analytics on that. So, 2.5 million transactions per second, 2.5 petabytes per day. Very, very interesting case study of very large scale, again, telematics, like for telecom. And there's a few others here. Well, ShareThrough is another one I definitely recommend. They're ad tech. They were the first published case study or first public usage of Spark Streaming. And they've done some pretty interesting work with like Algebird. It's an abstract algebra package out of Twitter. Really going back and using the math to get much better performance for streaming analytics. Okay, so with that, let me show a couple of things here. First off is one thing that's new for Spark Streaming in 1.2 is Python support. So before there had been Java and Scala support, but now you can integrate with Python. And just as an example, let's see here. I'm going to run netcat. And if I fire this up in a window here, and let me grab some kind of text. Wait a minute. I'll grab text out of here. Okay, so I've created a TCP socket with netcat, and I'm going to dump just a little bit of text in there. And now I'm going to go over here and run Spark Streaming. Let's see. Where's my, there we go. Can you all see this? Is that big enough? Okay, great. Classifiers there. PWD. Okay, great. Spark 1, 2. Okay, so I've got some code here. I'm going to run Spark Submit on this Python code. I'm going to hook up localhost port 9999. And what I'm going to run is right here. I set up a Spark Streaming context, and I tell it I'm just going to run locally on my laptop. So it says master equals local star. The streaming context is set for a window of 5 seconds. And I hook up to the host and the port for this socket. And then whatever comes in will create an RDD called lines. And I will run word count on that RDD in each microbatch window and print out the results. So if I run this, okay, it'll fire up, hopefully. I may have to change, yeah, I do have to change networking. Sorry about that. I'm moving my laptop all around, and I'm running OpenJDK 7 on a Mac, which has a bug. Spark local IP equals 127. So I'm going to jam this 7.0.0.1 there. So I'm going to force the local IP to localhost. Hopefully it'll get rid of that. Great. Okay, so now every 5 seconds, it's going to print out the results of running a microbatch. In this case, I'd cut and paste a paragraph of text into the socket, and so it's dumping out the word count for whatever comes in. I could put more in there, and it would update. Let me get some other text. Let's see here. How about some of this? Yeah, actually, it already caught it. So that's the idea, is that for every one of these time windows, you're going to get an RDD, you're going to apply some logic to it, and you'll be updating. Now, you might take that RDD and push it off into memory somewhere and use it later, or you might drop it into Cassandra or put it in HBase or someplace where you can use it historically. This is great for, like I say, machine data, rolling up log files, etc. Let me go into a slightly different demo. This one right here. I mentioned that there's some reference apps. So if you go to databricks.getbooks.io, there's a set of reference apps that we're building up. There's a couple. One is a log analyzer, and it's pretty good. It can handle a lot of different cases. The other one is this one. It's from Aaron Davidson's demo, really awesome demo called the Twitter Streaming Language Classifier. And the basic idea is this. We're going to hook up to Twitter. We're going to grab a bunch of tweets. And from the Twitter API, that's all JSON data. So we'll create a partition file of a bunch of JSON tweets. And then from there, we'll go in and we'll do a little bit of exploration in Spark SQL, and we'll kind of figure out what's inside the tweets, take a look at the language tags, what the distribution of that is, and use Spark SQL to do some data preparation and basically create a bunch of sparse vectors, one sparse vector for each tweet representing n-grams in the strings. And we'll train a machine learning model, k-means, an unsupervised model, to take a look and cluster based on the kinds of languages. And then from there, we'll create this data product, k-means model, and we'll put that and run it inside of Spark Streaming on the live Twitter results and be able to classify what the languages are. So we'll try to pick out some sort of language. So the first part of this is where we collect a bunch of tweets. And if you look at the code for that, it's basically, we've got a streaming context, and we're going to read JSON off of the Twitter utils and just basically capture whatever we get and drop it down into a file. So if I do that here, first off, grab this. Let me shut down what I was running here before. Okay. Okay. I'm going to go and grab a bunch of tweets and drop them in my temp directory. And I'll talk while this is running. This will take a little bit to run. What this is saying is it's going to run file interval. It's going to grab a file every 10 seconds, and it's going to collect 10,000 tweets. So I'm going to build up this big corpus of text to learn. And it's already started. If I take a look inside of here, ls temp, I've got tweets in there, and I've already got one started. Actually, it's more than that now. Okay, so it's building up some part files. If you take a look at what's in there, it's all going to be JSON. Just a bunch of JSON. Okay, so we'll let that run. What's going on over here in the code now is this is where the different parts of Spark start to come together. Once we've got a bunch of data, which we've gathered off of a pipe, off of tweets in a stream, the next thing we'll do is examine them. And we'll use Spark SQL to do that. So we're starting to combine streaming with SQL. What this is going to do, if I pull up the Scala, is first off, we're going to load up the JSON, and we're running this part in batch. We'll load up the JSON, and we'll take the RDD that we create out of the JSON, and we'll register it as a temp table with Spark SQL. So now we can do SQL queries on that RDD. Yeah. Pardon? Yeah. Sorry, is this, let me see if this is big enough. Is that easier to read? So the RDD is partitioned. So the RDD is bringing in a whole bunch of tweets out of these different part files. Right? And once you've got that, then you're taking the union of the schema across that JSON and using that to determine the schema of the tables. Yeah. No, the RDD will be this whole collection, and all the different partitions will be during some time period. So that's why we're going to collect a different partition every 10 seconds.
Okay, so that micro-batch.
Right.
Which is a part of
Yeah, this whole big partition. I'm doing it locally. You know, in HDFS, this would map very nicely out to distributed file system. Okay, so once we do this magic thing here with register temp table, then we can run queries. And so we'll take a look at the text and what languages are there, and then build up a histogram to show the distribution of languages that are coming in right now on Twitter. And then from there, we'll do some data preparation. We'll actually use Spark SQL to extract the text out and prepare it to run machine learning. And so now we've gone from streaming to Spark SQL to MLlib. And the way that we do this is for any text that comes in off of Twitter, we'll look at that string and we'll have a sliding window that goes across. And for every 2-letter sequence in the string, that's a bigram, we'll take the hash. We'll take the Java string hash for it and then take it modulo 1000. And so now we've converted a pair of characters into a number that ranges from 0 to 9999 and drop that into a sparse vector. So what this says is I can take any arbitrary string and populate this sparse vector. And that's interesting because, you know, if you can imagine all the different possible character combinations for all the different languages, that's a huge matrix. But in reality, you know, simplified Chinese is going to be over here, Arabic's going to be over here, Cyrillic is going to be over here, Latin's going to be over here. They all have their positions, right, in that vector space. And so we're going to leverage that. We're actually going to leverage the hash collisions to make this an easier problem to solve. Once we've got those vectors, we're going to run them in k-means down here. And so just this one line, basically train up the model. And then once we've got the model, we'll take it and convert it into an RDD and save it out as a file. This would be, you could save it out to, say, HDFS if you're running a cluster. And last but not least, we'll take and examine those clusters, see what we get inside the different clusters because it's unsupervised. You know, we're not telling it what to cluster in different places. We'll just have to see what's there. So let's see if this is running yet. Great. Great, that's run. And if we go back here and take a look, and no, I don't want that. We've got a lot of part files there to work with. Okay, so now what I'll do is this next step, the code that I showed, we'll take and examine it right here. We'll examine it and we'll train, and this will probably dump out a whole bunch of console, but I'll scroll back. So what I'm doing now is to read up all these tweets, and we'll just print out a bunch of them and see what's there. So we pre-print the JSON. And then from there, we'll load it up as schema in Spark SQL. So we'll print out the schema. So it's inherited this from the JSON. And they're pretty large. And from there, we'll start to sample and take a look through, see what's there. Definitely there's some hiragana. I see some locutar arabia, maybe a bit of Spanish, and there's some Korean, etc. Okay, great. Now let me scroll through because this is going to be kind of long. I should actually scroll down the bottom. Good. There's going to be a histogram that we printed out a little bit further up here, right here. So we can see that right now English is about 5,000 out of this set, and so about half of it. And then Japanese, Spanish, Portuguese, Arabic, Russian, Indonesian, Korean, etc. Kind of the usual suspects for like the top 10 this time of day. And then taking a look further, I will take no responsibility for whatsoever is happening on Twitter right now. But we'll see what the clusters have. Okay, so I need a Manny and a Petty tomorrow. That's cluster 1. Or sorry, cluster 0. Some of these will be a real mix, right? But some of them will have a pretty good signal. Cluster 1, for instance, has a lot of hiragana, katakana. So it's Japanese. And let's see here. Cluster 2, definitely English of a particular type. Cluster 3 is Arabic. And I think I'll probably go with Arabic because it's a little bit safer. Only a few of us can actually read what's going on there. Cluster 5 is a mix, and let's see, what was this one? Yeah, we'll stick with cluster 3. Okay. So now the next part of this is we're going to run the product that we've just built. Come on. Let's go back here a little bit. We're going to take what we just built out of k-means and apply it in real time. So we're going to build a Spark Streaming app that consumes this model and uses it to score the Twitter feed to figure out what language is being spoken or being written. So what we've got here is another streaming app, and it's going to go in and read in our k-means model and hook up to the Twitter stream. And then for every different tweet that comes in, it'll vectorize it the same way, create a sparse vector out of the tweet, and then take a look at the nearest cluster in k-means and use that to label it and figure out what language it is, and we'll filter on a particular language. So here we go. If I do predict, and oops, wait. I don't want that. I want to get cluster 3. Sorry. Here we go. Cluster 3. Okay, let's see how this works. So now I'm starting Spark Streaming again, and brought in the k-means model. And great. Okay, so now for every tweet that comes across, if it's closest to cluster 3, we're going to say it's Arabic, and we'll print that out and filter out the rest. Sound good? Okay. And I mean, if I've done commercial language products before, and I mean, in practice, I would probably do more of a segmented model with ensembles and using a lot of other signals and not just unsupervised learning. But for like 5 minutes, this is not bad for language classifying. Okay, I don't read enough of Al-Luqat al-Arabiyya to actually understand what's going on there, but oh, okay. Is there anything, Choice? It's up here. It's on live stream for posterity. Okay, good stuff. I'll just let that run. We'll see what we get. Oh, by the way, another thing, I'm not going to show this one right now, but if I take that same Python that I'd done earlier, one of the things I can do is change it to give it statefulness. And I think this is a really important aspect of Spark Streaming. So what I can do here is I've got a function, update func. That's a monoid. It's an addition monoid. And I will add another line here that says SSC checkpoint. So I'm going to checkpoint the state of my streaming application. And then the other change is that I go in and I do my word count, and a couple lines from the bottom it says update state by key. Whereas before I would just generate word count and dump it out to the console, here I'm going to update an internal RDD. And so for every word, I'm going to have a new count that comes in, and I will sum up those counts. And then the transform will operate on that and sort by key, and then we print it out. So essentially, we're keeping status in memory in an RDD, and every time through the microbatches, we'll be updating the internal key value pairs. So this is pretty cool because now you can build up some pretty substantial applications where you have running tallies, something of interest that you're monitoring. And that speaks toward more high availability kinds of issues. So I'll do that next. Well, I'll do it in a moment. One thing I will say is that there are a number of ways to integrate with Spark, and one of the things that we're seeing, particularly for streaming as being one of the more popular ones, is this pattern of having Kafka, Spark Streaming, and Cassandra. It really makes a lot of sense. Kafka gives you this distributed pipe, and then you hook up the receivers into Spark. And Spark Streaming pairs with that very nicely to do the big compute, the elastic compute. And then Cassandra pairs with that very nicely to take care of the storage underneath. The column store works very well for streaming. Cassandra really solves a lot of the problem that Google was trying to solve in 2002. Gets rid of the spinning disk failure problem quite nicely. These three work really well together. We're also seeing a lot of integration of, say, Spark Streaming and Elasticsearch, where you take your results and then dump them down into ES so you can query them fast later on. And also, we had questions earlier about this, but a really good pattern is to be using tachyon as a way of taking what I might have in an update state by key and publishing it out so that other apps can use it. Okay, so having said that, let's take a quick look ahead. I mentioned about high availability, and that's a big thing that's going in for Spark 1.2. A lot of this code has been in there. One of the things we do with Spark is that we have new code being added, and we will disable it by default. And it'll be out in the wild just to make sure that things are stable and working well. And then you can go back in and enable it. So we've already had parts of this for the past few releases. One of the things is that you had the ability to restart a driver since 1.1, and at least in Spark standalone mode. And so that's needed if you want to have high availability. What we're doing now in Spark 1.2 is to have two things, write-ahead logs and reliable receiver. So the thing with Spark Streaming is there's a lot of different moving parts. You've got the pipes coming in, you've got the receivers, you've got all the different nodes in your cluster, et cetera. If any of those go out, also you've got your driver managing it. If any of those parts go out, the whole thing's down, or you lose some data. So we're coming up with different ways to give robustness for each of these components. And you have to take into account the metadata for your app as well as the actual data that's streaming in. Now the metadata we can handle by checkpoints. The data streaming in, we handle that by reliable receiver plus a write-ahead log. And that way you can get zero data loss. There's a really great discussion of this. TD and Hari did a talk last week about it. So that's the YouTube link. They really go into a lot more detail. TD talks about the whole architecture, and Hari was working on Flume and Spark Streaming and the reliable receiver. But that's available for both Flume and Kafka. Moving beyond, one of the next things that will happen after 1.2 is out is backing off of some of this dependency on HDFS, so that like the write-ahead logs could be going into another layer, an abstract layer. Cassandra would be the natural thing to put in there. Yeah, question? It's part of it. So you can get the unreliable receiver, and that's much simpler code and higher throughput. You'll take some, by getting the high availability, you take a little bit of performance hit, but you can have multiple receivers to aggregate that. But it's in there. There's two different versions. And another thing is that Python support is there for writing streaming apps, but Kafka utils, Flume utils, those aren't done in Python yet, but we'll be following up with that, hopefully sooner than later. And lastly, the other thing that's really kind of driving a lot of this, the long-term goal is to have flow control. And that's a really hard problem when you're working on a cluster in real time. Again, there's a lot of moving parts. Having reliable flow control across multiple receivers is an extremely complex thing. But it's a hot area of research, and it's what we're driving towards. Not necessarily. We're looking at a lot of different things there of what will work out, and I don't believe that Akka Streams is really part of it yet. But, it's still to be written. How are we doing for time? Okay, cool. Let me shift gears a little bit. I want to talk a bit about, anybody here used approximation algorithms? So probabilistic data structures. I definitely want to introduce this because I think it's really important for streaming. It's part of what really makes sense for streaming. So if you look at, I come from more of like a data science background, machine learning and all, and leading data science teams. And if you look at the kind of stats that were really being pushed in the 19th and 20th century, they weren't about running on clusters. Okay, they were about working on paper. And they were really about defending some analysis that you make. So you get a bunch of numbers together, you take your sample, and you calculate your goodness of fit test for a particular distribution, et cetera, et cetera. It's about being able to defend what you've done. What changed in the early 2000s was kind of a shift towards more automated types of analytics, again, in a cluster computing context, Amazon, eBay, Google, LinkedIn, Facebook, et cetera. And that's much more about predictability. And as a result, there's emphasis on a very different kind of math that's evolved. I mean, a lot of what we were thinking about in terms of defensibility was tied to batch windows. You had to have the batch. So the subtle point is now we've had more math where a lot of our modeling can be based on probabilistic techniques, approximating. And the thing about it that really gets me is, when you're working with like a large cluster and terabytes of data and ginormous Hive queries, you're going to get your answers, and you're going to approximate them anyway, right? You're going to round up or however. And you'll use those parameters to plug into your machine learning models. So you've gone through a lot of extra work to get something that you approximate anyway. What makes a lot more sense would be to approximate in stream and get rid of the batch windows altogether. So that's the idea. Philippe Flageolet is one of the people who really pushed a lot of this. He's unfortunately passed away, but he was at INRI in Paris, and he wrote a lot of the early work in this area. Ilya Katsov did a nice article I'm showing here. The main idea is this. You trade off bounded error for the amount of resources it takes. So what this diagram is showing is for, say, count min sketch, 4% error if you've got a leaderboard of frequencies that you're tracking. If you trade off plus or minus 4% error bounds, you can drop the memory footprint by 2 orders of magnitude. Or you could change the resources in terms of time. But that's a game changer, because if we can take a really complex problem and fit it all into memory, now we can do this streaming stuff very, very well. And so you look at companies like Twitter, they've reworked their revenue apps based on these kinds of techniques pre-IPO. It's a real game changer. So the catchphrase there is hash, don't sample. Don't think about taking a sample. Think about how to hash, like we were showing before, taking the strings and hashing the bigrams. A lot of this gets into how you can really leverage the semi-group structure, the abstract algebra. And that's a really good reason to be working with something like Scala that has type safety and can really leverage that. Here's a few of the algorithms. You can do frequency summaries, ratios, if you will, with count min sketch. And there's some code for doing this in Spark. It's way too small. But here's something from a project called Algebird that Twitter did. This is a count min sketch that'll run nicely in Spark. Hyperlog is another one that's popular. It's a way of doing counters, but probabilistic counters. So rather than having to keep all the data for all the counters, you can just keep a table, and you can leverage hash collisions to make that table smaller. Leverage some error bounds to cut down the memory footprint, and then keep it all in memory. Bloom filters are real popular for set membership. This is used in a lot of big data projects. LSH and minhash are like that, but set similarity. DSQ is an example of streaming quantiles. So rather than taking a batch window and calculating the median out of a window, you can just do it in stream and get the median at any point in time. When you do anti-fraud, a lot of the times you want quantiles. You want to have velocities to plug into your fraud models. So this is a real game changer for that. And really, these are a new kind of data type that's evolving. You don't want to use it for everything, but for a lot of big data, being able to use these probabilistic data structures, you can think of it as a new kind of collection data type. The nice thing about it is that this does take advantage of, like I say, monoids and all. You can be doing your reads and writes in parallel, and you can be doing them at the same time. A few things that I'd point towards. Avi Bryant was one of the co-authors of Scalding and also for Algebird, and he was previously at Twitter. Nathan Mars used to work for Avi, and he brought him into Twitter. Of course, Nathan did Storm. Avi has this great talk from Strange Loop where he talks about this by leveraging some of the mathematical properties. You don't have to worry about how the data is grouped. You don't have to worry about how the data is ordered. You don't have to stop and take a batch window and sort it. You just take the data as it comes. And again, for streaming, that's a real game changer. I've got some other resources here that I'm going to point towards. Debashish Ghosh has some great links there that he's curating. Aggregate Knowledge, which is now Noistar, they did a mini conference on this. Titus Brown is using these techniques in genomics. But in general, I'd point towards the Algebird project at Twitter, especially for Scala. And there's also MMDS. Mining a Massive Datasets is a great book about related topics, but also there's a conference where a lot of this work is shown every other year. I'll have all these slides up on mine later on. But this really pairs well with streaming, and it's what we're trying to do for really fast analytics at scale. Okay, so shifting gears, let me just close up by having a few different resources. One is at Databricks, we're doing cloud-based notebooks. So how many people here have used IPython Notebook? So we're doing something like that, but it's got a Spark cluster behind it. And you can spin up or spin down within seconds. The idea is that you have a shared document, kind of like a Google spreadsheet. And you could have a team of 20 data scientists who are all looking at this in a browser window. And if one person changes a code cell and changes the output, everybody else sees it in real time. But it's all backed by a Spark cluster. So this is our commercial product at Databricks, and we can do a demo of that later on. Another thing is we've been working with O'Reilly to have the developer certificate program, and there are people here in the audience who were amongst the first crew. Sebastian actually was one of our volunteers for the beta test for this, one of the first people to take it. I'm the author for the exam, so if you have any questions about it, I'd love to help answer about this. But we've just started putting people through the exam. We're going to open it up online, hopefully within a week. Another thing is we've just announced we've got 2 MOOCs in the works with UCLA and UC Berkeley. So Anthony Joseph and Amit Talwalkar will be doing this starting early next year. Amit, actually MLlib was Amit's PhD work. So he'll be doing scalable machine learning. And we've got a lot of community links. Really, the Apache Spark email lists are the best place to get in front of the Apache committers working on Spark. They are there daily and answer a lot of questions. We're also curating a list of events worldwide about Spark and keeping track of videos for different meetups and talks, so it's a great resource. There's Spark Summit that's coming up. The next one will be in New York in March, and then San Francisco in June. And this thing has doubled every time we've done it, so we've had some pretty interesting growth. And a few different conferences coming up as well. Definitely Strata will be doing Spark Camp at Stratas and Spark Summits. On that note, I'll leave a couple of books up there and open it up to questions. Samir and I are here, and we can probably field a lot of different questions. Thank you very much. Oh, wait, we've got books. Yeah. Okay, cool. So asking me like a quiz kind of thing? Or is that? Okay. Good. Okay, good. Oh, yeah, what size t-shirt? Okay, good. So let's see. Analyzing the analyzers and the data. Okay, let's start with the Hive book. Does that sound good? Okay, so we've got some books courtesy of O'Reilly, a sponsor here, and we can give some of these away. Let's see. True or false? Spark is limited to 50-node clusters. Oh, who said that first? Oh, man. Okay. Okay, we'll have to have a harder question. Let's see. Man. Okay. Raise your hands. God, what's a good question? How about... Oh, yeah. Why is Hive called Hive? Bees? Any takers? We could do Cassandra.
So I'll just say why it is called Hive. If you think about a beehive, it's structured like this. And Hive is a project that analyzes structured data, structured files. So that's why it's called Hive. But I guess we'll have to think about a different question.
Okay, let's see. Okay, who is the author of Spark Streaming? Wait. Okay, winner. Good stuff. Congrats. Okay, this should be more rapid fire. We've got a bunch of these. Okay, let's see. Let's take the first 3 answers for Analyze the Analyzers. Some friends of ours, Harlan Harris, Sean Patrick Murphy, and Mark Bryson, they run the DC data community meetups back in DC. And they have a great book here, mini book from O'Reilly. So we got 3 of these. How about the Cassandra question? Can we ask where the name came from?
Test.
That's better. Sure. Why is it Cassandra called Cassandra? Why though? Another database company?
Yeah.
Does it start with yes?
Yeah, okay. How about the 3 of you get these, because you all helped answer it. Okay, awesome. Cheers. And can you pass that back? Okay. Okay, we got another one. Let's see, another question. Yes, 2013 Data Science Salary Survey, which proves that Spark salaries are higher. We have 4 of these. Let's see. Okay, what are the 6 languages that Spark can run in? Scala is 1. Who can answer all 6? Python. R. Close. Database. Huh? Okay, yeah. I'm going to just throw these out in the audience there, but you definitely get one. So, yeah, exactly. SQL would be the other. Yeah, there's Flambeau. There's a closure binding for it now, too. Okay, we need to give some other ones away. Let's see. What else can we... I don't want to give away the exam questions. Those are, like, too easy.
Why was Spark called Spark?
Oh, that's a great one.
It's interesting, but no. What? No. Nobody? It was a prototype project made to run on top of Mesos, the resource manager, and it was something just Matei wrote as a side project to kind of prove that like Mesos could run applications. So it was supposed to spark an ecosystem of applications on Mesos. Instead, Spark just became its own thing. So do I get one?
Yes, you get one. Okay, so Spark's out of Berkeley, and which is Berkeley's biggest rival? Yes, exactly. Okay, good. I heard twice. Who said that twice? I heard another one back there, too. Was there another Stanford? I'm from Stanford, anyway. What is the most active part of Spark out of all the components? What has the most contributors? MLib. Perfect. Okay. Another one.
Let's just see who asks good questions, and we'll get to them.
Actually, yeah. First good question. Let's open it up for Q&A. T-shirts, okay.
Let's just see who has good questions, and we'll give it to them.
That was
Okay,
fun.
go ahead in the back. Let me run this to you 1 sec.
I've been wondering how to go about putting Cassandra and Spark onto Meso.
Yeah.
How's the progress on that?
I haven't heard of anybody really wanting to do that. So, like, what is the reason that you're trying to do that?
No, there's good reasons.
I'm just bored, to be honest.
Well, I mean, data locality of the partitions, there would be a lot of good reason for that. The integration of Spark and Cassandra in DSC uses Spark standalone, so they're not going to be co-resident. It would make a lot of sense. It would make a lot of sense because they have very different needs on the JVMs to use containers and Mesos to just separate all that and run them locally on the same machines, all the different partitions. But I don't think that's quite available yet.
Okay.
But simply could get there. But are they? Well, I know they can run mixed workloads of both Mesos and then on top of that running Marathon and then launching Cassandra and Spark. The question is that the actual Spark Cassandra integration, does it take advantage of that? So that's the part.
Yeah, I mean, you would still get data locality if you're just running Spark with Cassandra using the connector. I don't know, I guess you would get more isolation of like JVM type stuff if you ran it with Mesos. I mean, I personally haven't heard of anybody working on it. There might be interesting things you can do if you get that working. Yeah.
Thank you.
Good stuff for mentioning Mesosphere. A shirt? Would you like a shirt? Okay, cool. Small and XL? Sounds good.
All right.
I used
Any
to
other
work for
questions?
Mesosphere, so yeah.
Go ahead.
Cool.
It's kind of related to is based on what you know. You guys hear me? What is the percentage of people running Spark standalone versus Mesos and versus Yarn? When I first started deploying, I was going through the same thing too. And what would be the advantages of using one versus another?
So there's actually 4 ways to run. There's local mode, which is good for prototyping. And if you run Spark in local mode, what happens is it launches a single JVM with the driver and the executor, and it runs your threads for Spark within it. There's no scalability with local mode. It's just one JVM. So the next step, it would be like Spark's standalone mode, which is using a scheduler that came with original Spark. In standalone mode, you have a slightly different architecture. You can scale your executors. You can have different executors on different machines. And in standalone mode, in addition to the different executors on different machines, you have a worker JVM that basically starts the executor. Right? So you have a worker that's tiny. It's like 400 megs of RAM or even less. And all it does is it starts an executor. Right? So you're kind of distributing your stuff, yourself out a little bit more now, and you have like a driver running totally separately on like a separate machine somewhere. Like your laptop is running a driver, and that driver is basically controlling the threads running inside your executors, and the way the executors start is with the worker JVM. So that's like standalone mode, and then there's Yarn. In Yarn, you also have an executor like on every machine, but in Yarn, you don't have the worker nodes, the worker JVM starting the executor. Instead, you have Yarn's node manager starting a container where the executor will run. So I mean, there's all these different ways you can run it. I would say that essentially it's really simple. If you're going to run against HDFS data in one of the big Hadoop distributions like Cloudera Yarn or Cloudera MapR or Hortonworks, you're probably going to use the Yarn integration, which is going to manage your executors for you. If you're going to use Cassandra, you're probably going to go with standalone mode because that's what DataStax is doing in their enterprise release. And then if you're doing something more unique, like building an application, perhaps you'll do Mesos. There are pros and cons about what you do. In Yarn, one of the major benefits is that you can dynamically scale up and down the number of executors. So what that means is that in standalone mode, like if you run in Cassandra, then you have to, in the beginning, when you start your Spark application, decide how many executors you will have. In a 20-node cluster, you should have at least 20 executors so that on every node, you can have data locality. So you have 20 executors at the very least in a 20-node cluster. Each executor starts up with a specific number of slots, meaning how many tasks it can run in the executor, which are threads. So you can start an executor with like 10 slots, so it can run 10 threads simultaneously, and you can start an executor with X amount of memory. Like I'll maybe start an executor with 4 gigs of memory each. So if you have a 20-node cluster and 20 executors running, each taking up 4 gigs of RAM, you're taking up a certain amount of resources in your cluster, and your application, your Spark application, will not give up those resources until you terminate the application. Even if in your application the usage of the executors goes up and down, it won't keep the executors. It will kind of greedily hog it. So the thing with Yarn you can do is when you start your application, you can decide. You can do this in Mesos as well. Only Yarn or Mesos supports this feature where you can say, I'm going to start my application with a minimum number of executors, which is just like 10. And it can grow to a maximum of 20, depending on the needs of the application. But it will start at 10, then like every few seconds or so, it'll add more executors. If there's a queue of tasks built up that need to be executed, and on the 10 executors, it cannot fulfill the queue, it keeps building up.
Auto-scaling.
What's that? It'll auto-scale.
Auto-scale.
Yeah, it'll auto-scale, but you as a developer cannot control the auto-scaling of the executors. You can't say, okay, at this point in my code, now I want to add 2 more executors. Instead, it's just if you have a buildup of tasks, it will automatically add executors for you until you get to max executors, which is a variable, maybe it's set to 20. And then what can happen, it can downscale as well. So if you have, the only way it downscales, once again, you as a developer cannot control this. Instead, if there is an executor, like number 19 executor, that is not running any tasks for a default of 30 seconds, then it'll auto-terminate that executor. It'll just get rid of it, and now you have 19 executors left, basically. So that's a big feature in Yarn you don't get in standalone mode. I think that all of them give you the ability to run Spark. Local is just prototyping, but the Yarn, Mesos, and standalone will all let you run Spark and give you access to everything within Spark, all the higher level libraries.
Based on what you see in production, like do you see a distribution of a lot?
I can talk a little bit about that, but I will say Andrew Orr is the committer who did the Elasticsearch, the auto-scaling that Samir was describing. And Andrew's going to do a talk next Monday at Galvanize in San Francisco. It'll be live streamed, but they're going to announce what they're doing for Elastic Spark in 1.2. And he's like the only person who really knows what's going on there yet, so that'll be good.
Yeah, I mean, if you want to know who's running the most, my opinion is probably like Yarn is going to be the biggest adopted, just because it's behind all the big Hadoop vendors.
Yeah, I mean,
It's like if you think that people who are going to run Spark right now are probably running it under CDH or Hortonworks or MapR, then they tend to dominate between the three of them, the big data space. And then it's maybe DataStax is the next vendor.
Well, I mean, the other thing though we've seen is that Yarn took a while to get out there, and there were a lot of Spark production applications in the wild before Yarn was available. So if you look at like a case study of say like Media Crossing or HubSpot, they're running on Mesos. Because in production they could do that well long before Yarn. Mesos is a lot more mature product. If you look, there's a case study from Sriram Krishnan, who runs the data team at Twitter earlier this year, did a talk in Seattle at the Seattle Big Data Meetup about their side-by-side comparisons of revenue apps in either Pig or Scalding and Spark. And they were running them on Yarn clusters, but the interesting thing is that they have a lot of hands-on with both Yarn and Mesos. So they made some comments about the comparisons there. I don't believe that they're running on Mesos for Spark yet, but they do. Well, their services infrastructure is Mesos, and any new services going on. Their big data side, they had a existing Hadoop practice. So that's a pretty good one to look at.
They haven't run it on Mesos just because of like lack of time, or they have.
Well, they have this whole big infrastructure that is running out on their Hadoop clusters, and I don't think that they're really eager to just get rid of that because all their stuff runs on it. But they do have a lot of hands on Mesos, and I'm sure they run it on their Mesos clusters. Both Netflix and eBay have also published about Mesos usage, and they're both using Spark. So I would be curious to drill down on those and see what they're doing too.
Thanks a lot.
Go ahead.
There were two gentlemen from Oyala that gave a talk.
Yeah, they do too.
One of the points they mentioned was, I believe that in Spark Streaming, each executor by default eats up 380 x megabytes of memory. Is that still true? What have you heard of that before? And then the second question I had, I was going to ask about Elastic Spark, but it looks like that's still. And is that coming out in 1.2?
Yeah. Okay. Elastic Spark is coming out in 1.2. The talk will be Monday evening, and we'll have that archived. But if you want to if you want to catch the live stream, it'll be published on Monday. As far as the running Spark Streaming, the requirement there is just that you're going to use a task slot per executor for the receiver. So they may have been talking about that, but that's not actually.
I think they mentioned there was like a specific amount of overhead in the range of 300 megabytes.
Yeah,
per
I mean
executor.
That's not actually huge when you take
it's
a look.
Yeah, it's not huge, but just
the thing that happens in Yarn, like I think what happens is like if you say to Yarn, or in like your Cloudera or like your Hadoop configuration, you say that you want your executor memory to be, let's say, 400 megabytes. I think it doesn't actually make it 400 megabytes. There's like a minimum number it will always have, which is something in the range of 300 megs. Okay. Then your 400 is like on top of that. It's something more like that. It's a little bit more nuanced. Yeah, I mean, it's probably something good we should change down the line, because if you set it to 400, that's what you're assuming your total JVM heap memory will be, and it's not exactly like that. I saw that in Yarn. I'm not sure if that's
it was specific to Yarn.
Was that Al Toby's talk?
Yeah.
Yeah, okay.
Yeah.
He's at DataStax now, but yeah, we could check with him.
And then there's, I also heard there's a 3-second kind of, it always waits 3 seconds before it actually starts.
Before it starts out, streaming has to get all the plumbing going and all that.
Yeah.
Yeah, there's a little bit of delay there. Although, I mean, that's the thing we're trying to do with high availability is make it restart much faster. So if you've got the checkpointed metadata and you've got the receivers that are running reliable receivers, then you can get going much, much faster. Pick up from the last state. Yeah, you could see that too. When I was running here, it took a couple seconds to get going. Yeah, we haven't been giving out, would you like small t-shirts or both?
Oh, the small t-shirt.
Okay, sounds good.
In Spark Streaming, the driver has to serialize the function and keep sending it to the executor. So you're probably seeing a delay on that. Like every time a new RDD comes into the stream, it has to get a function to be applied upon it. And it's like, are you talking about just in the very beginning when you start the Spark Streaming, or? Yeah, I mean, there's always going to be a little bit of overhead in just starting out these distributed applications. I think that's in general probably normal. Yeah.
There's also a Jira ticket that they did a little bit of code. there any plan to work on that, or is it just going to stay?
What resources was Spark letting go of?
So, for example,
No, I think I heard about that.
yeah.
No,